Okay, so we will discuss example 7.1 now to apply the concepts which we have learned in the previous class. So you have a steel beam of a 25 mm width and 75 mm deep. So you have this 25 mm wide and 75 mm deep is pinned to supports at points A and B. You have pinned to supports at A and B, where the support B is on rollers. Okay, this is on a roller and it is free to move horizontally. When the ends of the beam are loaded with 5 kilonewton loads, this end and this end, we wish to find the maximum bending stress at the mid span of the beam. So this is called the mid span, and you should know, I mean, span is a word used in bridges, which are essentially beams. Okay, so what is a mid span? It would be middle of it. So this word you should be comfortable with, and you can see how it is used in bridges by looking up on the internet some pictures or videos perhaps. Okay. Okay, and also the angle delta phi naught subtended by the cross sections at A and B in the deformed beam. So this is the delta phi naught, which after curvature this will be formed. Earlier this angle would have been not present, okay, because A and B in the undeformed case would never meet. Okay, now let's see how we can get along with this problem. We attack this problem as usual within the framework of 2.1. I mean, as I had said, that was one thing which kept on coming again and again. Our first step is to determine the bending moment, which is required to satisfy the equilibrium equations at each point along the beam. This is shown in diagram this one. Okay, so you have found out the bending moment, which you have known how to find earlier. Okay, and that is how the bending moment varies along the length of the beam. So this, how to draw this bending moment diagram, is something which we have learned in the earlier chapter, so we are not going to that again. If you have a doubt, please stop this lecture right away and go back and see how with this you can draw this. Okay, this is something by this time you should be able to draw. Okay, now from this diagram, we see that the central portion AB is one of constant bending moment. So this part of the beam is having an MB which is constant. Does it help us in any way? Yes, I mean, because the bending moment is constant in this part, this can be assumed to be pure bending, and hence all the assumptions which we were applying, all the theories which we have developed will all be valid now. Okay, so we cannot just look at a problem, say like this problem, and assume pure bending right away. There has to be reason for doing that, and in that case we have found that out. Okay, so the AB part of the beam is under pure bending, and that will be much helpful for us. Now to calculate the stress from 716, we must locate the coordinate axis to calculate IZZ. So you have this cross section of the beam, this one. Okay, if you are trying to look at it from this side, and you want to find where the neutral axis would form, okay, would be there. Now you have to calculate this IZZ. For this, you take a area delta A like this one, this shaded area, which is at a distance of y, and the length is delta y, the width is b, width is finite, this is delta y. So that would uh, help us find IZZ. That would be from minus h by 2 to h by 2. Eventually you have to write it for the whole area. Okay, but you can write the delta A into what? Delta Y into B. So IZZ then can be found out for the whole area of this surface as y square into B dy, and this should be equal to BH cube by 12. You knew this perhaps from your earlier knowledge of how to calculate the area moments. So that is also evident in this equation. So you can use equation 713. So 713 was IZZ is equal to y square dA into A. This was 713. Okay, so once this is done, you would find a numerical value of what IZZ is, and then you will have to just find the maximum value of the bending stress. So look at the bending stress, that is minus mb by y into IZZ. So IZZ is something which you have found out. Okay, mb will have its value which you already know, that is constant and is equal to minus 1.5 kilonewton meter. Okay, and then the only thing left out is to for this to be maximum. Okay, this must be maximum. So what would be the maximum value of it? It would be at the top part of it, meaning over here or over here if you take the negative sign. So y must be equal to h by 2 for maximum sigma x, sigma x. Okay, so at mid span the bending stress at the top of the beam is found out to be this. So if you take it, if you take a positive y, you will get this value as 64 Newton, mn by meter square, and if you take a minus 37.5 or minus h by 2, you will get a negative value. Now the next part is to be able to find the this angle delta phi naught. Okay, so and this can also be seen as the change in angle, because earlier there was no angle between them and now you have found this, so you can do it either way. So for this, let's start using the equation 714, which is d phi by ds, and that is equal to mb by ei z. Okay, so this is something which is known. Okay, and this is something which is given to you for the steel. Okay, if it's not given in the question, you will have to look it up from one of the tables and then use this value. Okay, so it's given a steel beam, so the material is given, and IZZ is something which you have calculated, so this should give you the angle. Okay, and this must be negative because the curvature is of this form. If the curvature had formed like this, then it would be a positive. And to ensure that this is negative, the only thing which you can play with is MB. So you must use a negative sign over there. Okay. Okay, so that solves the problem, because I mean when this formula was derived, this one, the curvature was assumed like this, but you have a curvature of this kind, so there must be a negative sign. That's the only thing which has. Okay, so this is done, and then all you have to do is do this integration. So you will have to write it as from point A to B, and you should be able to write this value. So ds you can easily write, and you will get a value of it. Once that is done, you will be able to find rho which is essentially 1 by d phi by ds, or d phi by ds is equal to 1 by rho. So this is what is eventually found out from you. So once you have found the angle phi naught, you should be able to find this. And anyways, d phi by ds is something which you have from here. Okay, so that's example 7.1. With this you could find the maximum bending stress. And again, just to recall, why would we want to find the maximum bending stress? The reason is, this tells you that that will be maximum over here and over here. So if there is any failure which has to happen, it will happen in this beam at these places. Okay? They will happen first over there. Okay. Now let's move to problem 7, example 7.2. You want to do something similar. You want to find the maximum tensile and compressive bending stresses in the symmetrical T beam. So this is a T beam. Okay, there is a T you can see over here. This is the T which forms. It's a T beam. And we had seen L beam. There are I beams. There are H beams. So lots of beams, and many of them are used in the construction activities. So you can ever, if you do look up any construction happening around, please have a look and see the shape of the beam. Okay. Anyways, so you have a T beam over here, and this qualifies to be a beam such that there is a plane of symmetry and the beam is symmetric about that. Okay. So this is the plane of symmetry. So one half is this, the other half goes on the other side. So it is symmetric about that. We want to find the maximum tensile and compressive bending stresses, sigma x over there, and under the action of a constant bending moment. So here in this problem, you are given from the start itself that the bending moment is constant throughout. So you can assume pure bending. In the last problem, you remember you had to actually find the bending moment. And then there was a region which was in the middle, which was under pure bending. In this case, you are already given. Okay, so 716 is what we would want to use, just like always. So it looks a very easy paragraph as such, right? Easy sort of formula, the one which I am writing right now, which is 716. But knowing this is not enough. To be able to effectively use it, you must know the theory through which we have arrived. You must very carefully know the assumptions of this and check whether the problem which you are solving using this formula is not violating any of those assumptions. Okay, so it's a long way when we had come here, and those things have to be kept in mind when you solve a problem. Okay, so the evaluation of IZZ is something which we must do for this beam, and again, using your knowledge of mechanics, I think you should be able to find IZZ. So let me just go through that part. You recall how it's done. You take one part, find IZZ of that, then you take the second part, find IZZ of that. Okay, that's how you had done before. You used to break it down, and you could also do it like if you take it for the whole this cuboid and then remove from here, and there are many ways to go about this problem. Okay, so in figure 7.12b, we want to show this, that we consider the beam to be made up of a rectangle 1. This is rectangle 1 from here to here, and this is rectangle 2, and you want to now find we consider the beam to be rectangle 1, and this has dimensions b by 2h, so b by 2h, and the other is h by 2 into 6b. Okay, we let y bar represent the distance from the base to the centroid of the cross section. So y bar is the distance from the base to the centroid of the cross section. So y bar is equal to y1ai to ai, where I will be 1 to 2. Okay, so you have to sum it over both cases, and this you can find out. And once this is done, you can use the parallel axis theorem to find izz1, then izz2. Again, we are not going through the details of it because it is assumed that you would be very good at it after doing APL 100. If there is any shred of a doubt, please do this from your APL 100 knowledge and then come back to this so that you are clear on this, because it is very unlikely you will get a geometry which you have seen before. So the only way is to be able to find them using the methods which you have learned before, and hence izz will go izz1, sorry, so izz will be equal to izz1 plus izz2. Okay, so that's how you would solve. And once you have izz, you have to just substitute over here the bending moment. In terms of the bending moment, you will have this, and y is something which you can always put out there. Okay, so you have to use a y equal to minus 3h by 4, which was essentially this y bar which you had found out. So this was where your neutral surface was. Okay, so called the neutral surface. Okay, so that's where you would go about, and y is equal to 3h by 4, and you will assume it to be a minus or a plus depending on whether you want to find the compressive bending stress or the tensile bending stress. So y bar is actually equal to 3h by 4. Okay, so this is how we find the stress distribution, and you can see them in this figure over here. Okay, so the neutral surface is found out over here, 3h by 4, and in this figure, so obviously the stress will always be 0 on the neutral axis, sigma x, and then above part of it will be compressing, so you have the stress like this part will be extensing, so you have the stress like this, and both of this you are easily able to find out. Okay, so that is how we can apply this to a shape which is, as you have seen, an I-shaped beam. So moving on, let's move to section 7.6. This particular section is dedicated to the stresses in symmetrical elastic beams transmitting both shear force and bending moment. So you have both shear force and bending moment, and this is where this combination of various forms of loading is coming into the picture. Okay, we had seen slightly in the last chapter where both twisting and axial force was applied. In this case, we are adding a shear force to the bending. Okay, in this situation, so until now we haven't taken this the shear force due to bending, and now we want to learn that situation as well. So, and this is not pure bending, that's the first part. Okay, this sort of frees us from the assumption when the MB is not constant throughout. Okay, so pure bending is a relatively uncommon type of loading for a beam. Most of the time you would have a bending moment which will vary along the length of the beam. As we have seen in chapter 3, it is much more common for a shear force to be present, as illustrated in figure 7.2a. So if you have 7.2a, let's see. Okay, this is the most common situation where you have bending moment and shear force. Now, can you recall how did we not consider shear force until now? Okay, can you go back to the textbook and see at which state we found it was okay to drop this? Okay, so please do that once. Okay, now it is more difficult to obtain an exact solution to this problem, since the presence of a shear force means that the bending moment varies along the beam, and hence many of the symmetry arguments of section 7.2, I mean right from the start of this chapter we used symmetry and we created equations and ideas based on that. But since pure bending is not there, since bending moment will not, and if you recall that A1D1 segment which would cause a bump, that was the start of the symmetry arguments. They were there because the same MB was acting on both the surfaces at this end and the other end as well of those two small elements. So none of them are valid, and hence we will now have this situation, okay, where exact solutions will be difficult. So there is another way in which we use some advanced concepts of elasticity to solve this, okay, but that we are not doing in this course. This course is not meant for that. So what we will do here is we shall describe what is frequently referred to as the engineering theory of stresses in beams. So okay, to distinguish from the elasticity theory mentioned in the preceding paragraph. So the elasticity theory is a very rigorous mathematically and it's somewhat more suited to a course which is more advanced level to this. Okay, we will use somewhat of an engineering theory, and this is definitely a weaker theory. Please don't see that what you are learning is just an alternate of the other one. I mean, if it was giving you the exactly right answers, you wouldn't have to worry about this. But in most of the advanced applications, this is something which you use. Okay, in many research and development methods, you only go with the elasticity theory. But since there are many other places where this theory and the results given by this engineering theory, which is weaker than the actual elasticity theory, works, we will study this over here. So let's see how we can develop this theory. To develop this engineering theory, we make the assumption that the bending stress distribution 7.16 is valid sorry so 7.16 sigma x is minus mby by izz. You have to assume that this is valid. This is valid even when MB is not constant along the length, okay, or the presence of shear force. So this is an assumption which is being taken. I'll stop a few seconds before you can let this assumption sink in. So once you make this assumption, actually it is better for you to write it like this. Okay, and clearly then your sigma x will depend on x and y. This is an assumption of this theory. The reason it's better to write it like this is so that you get comfortable that mb is not a constant anymore, it's a function of x. Okay, so after this it's practically the same method. You apply the equilibrium concepts and eventually you would want to find the stresses inside the beam when mb is a function of x. So let's see how we can do that. Then by requiring that the equilibrium be satisfied for certain well selected free bodies, we can estimate the stress distribution which has the shear force as its resultant. Since we do not include the satisfaction of geometric compatibility and satisfaction of the stress strain relations in our analysis, we have no a priori certainty that the results are accurate. This is important. Okay. However, see, this is the thing. I mean, you are only getting the stress field using this approximation assumption. You are not ensuring geometric compatibility, you are not ensuring that the stress and the strain relationships are there. So there is no guarantee that your answers are correct. You are only doing, say, one step out of those 2.1. However, experimental evidence and comparison with some of the aforementioned solutions from the elasticity show that the estimates of this stress distribution are reasonable for engineering purposes. Okay, you don't have to nitpick on this method just because of some of the steps which are missing, and it has been reasonably shown to work. Okay, so many of the things around you have been designed using this theory, despite the fact that more accurate theories are available. Okay, now beginning our analysis, we show in figure 713a. Let's see 713a. 713a, a length delta x of a beam which is subjected to both bending and shear. Okay, so there is definitely a bending and then there is shear. Okay, now there are certain changes in the symbols and we see what is there. We take the case where there is no external transverse load acting on the element, so the transverse shear force V is independent of x. Let's take a case where V of x is constant, and the reason for that is there is no transverse force acting on your beam. Okay, so I mean there is nothing like this. That is not there for you as an external loading. It can be present inside, right, but not because you are applying. So there is no reason for it to vary along the x. If it had to vary, then it would go from v1 to v2, but there is no reason for it to vary, so it will be constant, present but constant. And a variation in bending moment with x is represented by the increment delta mb. So you have mb over here, and on this face it will be mb plus delta mb. So this is similar to, if you remember, one face we had taken what sigma x, and on the other sigma x, and if the element was delta x, it would be sigma x plus delta sigma x, and the same would be for the other components. We had done this at some point in our course, I think in chapter 4. Okay, so this is what we do with, so that's how we draw 7.13a. Now we assume that the bending stresses are given by 716. This is the one, this is there as indicated diagrammatically in the sketch in 7.13b. Due to increased delta mb in the bending moment over the length delta x, the bending stress acting on the positive x face of the beam element will be somewhat larger than those on the negative x face. Okay, so because the stress on this face could have been written as sigma x equal to minus mb by y I z z. On this face it would be sigma x equal to minus mb plus delta mb. Okay, y by I z z. So this is what we mean, that the bending stresses acting on the positive x phase will be somewhat larger. So you have this, and because the contribution is coming from this delta mb term, so this is larger than this in magnitude wise. Okay, so let's drop this. That is seen in this cases, and over here also this is larger compared to this. In the previous case they would be of the exact same length. The directions will be different, but they would be of the exact same length. They are still trying to sort of extend this part and contract this part, but by these different stresses now, and that difference in stresses is coming because the MB is varying with X. Okay. We next consider the equilibrium of this segment uh, of the beam shown in figure 713C, which we obtain by isolating that part of the beam element of figure 7.13b above the plane defined by y is equal to y1. So take a part of the beam which is taken from a distance over here and y1. So that is what we have done over here. So it's like one part which has been cut out from the top. So we are only taking this part. Okay. Now we can focus our attention on this is C. Now due to the unbalance of bending stress on the ends of this segment, there must be a force. So remember, I mean, this side of the force is large, the stress is large, and this side is small. So there is an unbalance and you want them to be in equilibrium. The only way that can happen is you have this additional force delta F yx. Okay, why is it acting at, so it is acting at the bottom of this, at the bottom part of this plane. Okay, at the bottom part of this cutout section, so it's acting on the plane below this. That's why it's shown with a dotted sign, because we can't really see it from this view, it's hidden. Okay, so once you have this acting, this will balance out this difference, and what it will do is it will act obviously on the y equal to something plane in the x direction. Okay, so that is why it is there like this. Okay, so this is where, and now you express the equilibrium requirement in quantitative form. So let's see, there's one more line. There must be a force delta Fyx acting on the negative y phase to obtain force balance. Okay, so this is the top is the positive y phase and the bottom is the negative y phase. This is the positive y phase, so that's acting in the negative phi phase. We show this positive shear force delta Fyx in the negative x direction, consistent with the fact that the phase on which it acts is a negative phi phase. So this is important. I mean, you can always wonder, why am I showing the force like this? You have to take care of the fact that you are acting on the negative phase now. So for this to be positive, it has to act in this manner. Okay, so this was very similar to this thing which we had done earlier. How would you find the directions? So if you can go back to chapter, I think 2 3, perhaps 3, where this was done, the same idea has to happen. So for delta Fyx to be positive, since it's acting on a negative phase, it must act in the negative x direction. Now you express this equilibrium requirement in the quantitative form. So sigma Fx will be equal to sigma x dA, and you would want this on A1. Okay, so this is over here. This area is what I'm talking about. Okay, and then you have a minus of delta fyx. Okay, and then you have, so sorry, this force, it's always the force, so this force is actually this one. Okay, now minus fyx is this one, and then you have another a1, so the area is the same, and then you would have a sigma x dA. Okay, and this must act on x, this acts on x plus delta x. Okay, so this is x clearly, and this is x plus delta x. Okay, so this is 7.18 of your textbook, and you can go from y equal to y1 to y equal to c and find out the delta fx. Okay, and then substitute this into 7.7, it substitute 7.16, I think, which was this assumption which you had made, this one. Okay, into 7. This one 7.19, and then you would be able to find this relation, which is dfyx into dx when this delta x is small. Okay, when this delta x tends to 0, you will be able to write minus dmb by dx 1 by I z z a1 y dA. Okay, now once you have done this, you have to substitute the moment equilibrium requirement 3.112 for the beam of element 713A. What would that give you? So 3.12, I mean, if you go back to the moment equilibrium requirement, and then you would put that in 7.13A. 7.13A is 7.13 is, okay, you would get the moment equilibrium, so it would be dmb. Let me just write it more clearly. I think it's not a good way to do this. Let me just expand it slightly so that, yeah, now we have enough space. So let's start where we were, just to make sure that we don't miss out on any step. We had done the force balance, so we'll start from there, and I'll be now using this whole space around me. Okay,